going to apologize for, well, no, yeah, then we can see. I'm going to apologize first for the not very good state of these slides, but that's part of the story of this talk. I had these thoughts and wrote them down, and in trying to teach them and lecture on them, I quickly discovered that no one understood what I was talking about at all. And in trying to think of a audience that might be receptive to it, the infometrics audience seemed like it was the only hope. So a couple of years ago, I gave a preliminary version of this talk, but unfortunately at that time, the slides came out with very small type, and I don't think anybody understood anything of what I said. So I thought I'd give it one more shot, and this is it. But I still can't get Mathematica slides to transfer to PDF without problems. Also, in the interest of disclosure, I'm not actually an external faculty member at Santa Fe Institute anymore. I was, but no, that's not what I wanted to do. I don't think this is, all right, it's that. No. Nope. I somehow got it on. Okay, so let me summarize what this is. This is, in formal terms, a very simple exercise, which is to take the Bayesian, the formula for updating Bayesian priors to posteriors as a framework for understanding what we do when we choose a theory on the basis of data as evidence in a very general setting. So the only advantage of this kind of work is kind of philosophical. That is to try to understand abstractly what we're trying to do in general when we do this kind of theoretical science. The basic theme of this is that there's a one-to-one connection between the notion of information compression and posterior probability. So that's one point that I'd like to bring out. A second is to use a notion of theory, which as a set of ensembles, as an ensemble idea, which comes from the work on effective complexity that Murray Gell-Mann and Seth Lloyd developed. My interest is not so much in measures of complexity, it's more in the picture that they give of what a theory is and how it works. And I'd like to acknowledge that I've had the very good fortune to be able to discuss some of these ideas with Gell-Mann and Lloyd, which was eye-opening, and I hope will seep down to your understanding of these things. The main point there is that it was very hard for me to understand, and I think it's very hard for other people to understand who are not physicists, the importance of constraints in disciplining this problem of theory choice. So that's a point that I'd like to highlight. And the final point is that entropy maximization does appear in this story, but it appears in a rather unusual guise, an information theory guise, basically because entropy is a way of coding, of getting a Shannon coding of frequency distributions, and therefore makes the second law of thermodynamics appear to be more of an empirical law, that is one that would apply for particular entropies rather than some kind of a universal phenomenon. So we're going to start with the logarithmic form of Bayes' theorem, which is just that the log of the posterior probability of a hypothesis or theory given data is equal to the log of the prior plus the log of the likelihood minus the normalizing factor. The D in this case is going to just be thought of as a string of any length that describes what we know about the world or the part of the world that we're interested in. H is some theory that offers an explanation of the data. So we can also think of any theory as the basis of a two-part code. This is where there's a strong intersection of this way of looking at things with Peter Adrian's idea of facticity as well. The idea here is that you transmit the theory as the first part of the code, as a model for the data, and then given the theory, if the theory is a reasonably good theory, you can then transmit the data in a highly compressed form, or much more compressed form, as the result. And you can see that this equation 1 can actually be thought of as a two-part code. The two parts are the transmission of the theory, and the second is the transmission of the data given using the theory as the model. So the maximum posterior probability is the same thing as the shortest to minimum description length of Reason and Wallace and Bolton. What do we mean by theory? Well, this is where I'm going to take some ideas from Gelman and Lloyd. Their idea is that theory is basically an assignment of frequencies to the set of all data strings of a certain length. So the notion here is that the ensemble assigns a frequency to every data string. And in that case, the ensemble itself becomes the likelihood. So given the ensemble as a theory, the probability of the data string is just the probability that the ensemble assigns to it. So we now have the two-part code in the form of the bits required to describe the ensemble, and then the bits required to pick out the data string given the ensemble itself. So what we need now is a prior over ensembles. And the prior that I'm going to use actually has a wonderful history going back to Ray Solomonoff and Kolmogorov, but the idea of it is that the prior is not a judgment about the likelihood of any particular data string. The prior is actually an attitude towards simplicity in theory formation. And the attitude is that simpler theories are better. It's basically the attitude of Occam's razor, and it's expressed in this universal prior by saying that the prior probability of a hypothesis is equal to 2 to the minus k of h, where k is the Kolmogorov complexity of the prior. So we say of the theory. So we say it takes a certain amount of bits loaded onto a universal Turing machine to calculate the ensemble probabilities. And the more bits of that type, the less we like the theory to start with. Then we consider how well it does with the data, okay? And you trade those two facts off. Simple hypotheses correspond to shorter programs. If you stop and think about what a program has to do to compute an ensemble frequencies, it falls out into two pieces. The first subprogram is going to sort the data strings into subclasses according to some criterion. For example, if it's statistical mechanics in the simplest form of the canonical ensemble of Gibbs, the machine sorts it on the basis of the energy levels of the state of each state. So the first thing you do is you sort it into these different categories. The second ensemble subprogram is going to assign a frequency to each of these bins, each of these subcategories. Once the program's done that, it's got to assign the same frequency to all of the strings in any bin because it can't tell the difference between them. If you wanted to tell the difference between them, you'd have to write a longer program, a more complicated theory that made a finer set of distinctions. So the ensemble can be described by the bins that it puts the strings in and by the frequency it assigns to the bins. Then the constraints, and this is the point that I stumbled on and that Murray Gell-Mann helped me with. In statistical mechanics, constraints are crucial to making these theories work. So the type of constraint that you have is that the expectation of some function, maybe energy or income or whatever it is that you're interested in, has to meet some previously known value. And this is very important practically, and that's just one of the things I wanted to emphasize. If you leave out this constraint, this whole thing falls out. It's a perfectly valid theory, but what happens is that you get programs that just sort the data string into the smallest possible set of its own and put everything else in the other set, and that's okay, but it's not much of a theory. So it almost always turns out that it's the addition of these constraints that gives some real richness and drama to this kind of theory. So the AIC of the ensemble is the sum of the length of the code words necessary to describe each program, a certain amount of code for the program that sorts the strings, and a certain amount of bits for the frequency distribution that you assign on the strings. And that's where, as far as I can see, entropy comes into the story. And it's a rather unusual place. The reason that you might want to maximize entropy is because you can base a Shannon coding of frequency distributions on their entropy. For example, we could start with high entropy ones and we'll give the shortest code words to the highest entropy strings and work our way down. And then we would have a way to Shannon code. And that might turn out, in fact, to be the most efficient way to do this for some data strings. But it might be that we would want to go up from the bottom, go from minimum entropy to maximum entropy. Or we might want to use, instead of Shannon entropy, we might want to use alternative entropies like Solis's entropy. Okay, so we then get the formula for the bits that are involved, which is that what you're trying to minimize is, well, maximize is the posterior probability. You count against it the complexity of the sorting program. You count for it the entity of the frequency distribution, less than the maximum entropy. And then you also give it some credit for putting the data string with a high probability. And against it is what I call the residual entropy, that is the number of other data strings that are in the same bin with the other candidate strings in the same bin. Okay, so that's actually the core of the ideas. And maybe in the discussion we can have a little bit more exploration of this idea. I'll just quickly flip through some points that I think are worth thinking about. One is, where does the second law of thermodynamics fit into this scheme? We saw how it fit into Ariel's scheme the other yesterday. What does this say about which definition of entropy? How about neuroscience? Is the Turing machine the only model for generating these sorting algorithms of strings? Well, no, it isn't, and in fact, neuroscientists have their own ways of sorting models of creation of these ensembles, or ensemble-like systems. Philosophy of science, the main point here is that if you buy this, it means that you're always going to be dealing with a coarse graining of reality, or almost always. It's only if you have a very lucky hit that you're not going to see any particular object as kind of part of a whole set of rather similar objects which you give similar probability to. This is not a cookbook, and we could talk about that and the fact that the Kolmogorov AIC is not a computable function. Okay, thank you.